Yeah, we're right on time, so we'll get started. This is where we left off on Monday, where we had a rectangle function that is annotated either rectx or this sort of character x, and we discussed the fact that its Fourier transform is a sinc function, and so these are Fourier pairs or conjugate functions. So this shows up a lot in, for example, the point spread function of NMR imaging is a sinc function if you acquire data in a rectangular way in Fourier space. So it'll be a very important function for us. Um, Normally, if we look at this in Fourier space, we're going to call that K, which is a spatial frequency. So for most of the course, most of the examples we'll try and keep the Fourier space labeled with the value K, which is spatial frequency in cycles per centimeter or something like that. We can write the rectangle function as a two-dimensional function. And so now as I'm going along X, and I come up to minus 1/2 x. After I pass it, the function goes to 1. And then after I pass 1/2, it comes back down to 0. Same thing happens in y, leaving us with this box or a square centered on the origin. And that's just the product of two rect functions, one-dimensional rect functions. You can take the Fourier transform of this two-dimensional function, and you get this multiplication of two sinc functions. It looks like this. It has a peak at the origin, and just like a sinc function along x, it oscillates up and down as we go along the axis. Excuse me. Same in y. This really isn't a sombrero function that would have sort of circular symmetry around the origin. That would occur if this was a circle. It's not a circle, so you get this function, which is not circularly symmetric as the Fourier transform. We're going to use complex numbers a lot, so just a quick review how they work. We can think of these numbers as a position in the complex plane where we have a real component to the number x and then the imaginary component y, and we write the number itself as the sum of these two things. The magnitude of this vector, of this complex vector, is the magnitude of the complex number, and this is its phase. And so if you give a magnitude and a phase, you can uniquely give yourself a location in the complex plane. And so to figure out the magnitude of a complex number, we can just take the square of the components, take the square root, and that's our magnitude. And the phase angle is the arctangent of the imaginary part over the real part. And so in this case, it was 63 degrees. Um, Also, j squared equals -1. And if we have a complex number that it has a real part and an imaginary part, and another complex number with a real and imaginary, to multiply those two numbers together, we just do it as you would with algebra. Multiply this real times this and this real times the imaginary part and expand that out. Um, and that turns into something like this, where when you multiply a j times a j, the j squared gives you the -1. And so this multiplication of these two complex numbers, they're two vectors in the complex plane, gives you a real number. So that's a point on the horizontal or the x-axis. This equation, it's called Euler's formula. It's a true equation, and it's not like a definition. It's an actual equation that states that e to the j theta is equal to cos theta plus j sine theta. And you just think about that for a second and say, what does that mean? So we all know what e to the x is, right? If x was a real value up here, we know e to the x is the function that is its own derivative. So when you take the derivative of e to the x, you get e to the x back as that derivative. when we put uh, a complex number up here in the argument for e to the x, we can show its definition gives us cos theta as the real part and j sine theta as the imaginary part of this complex number. And the magnet, you can also write it as the magnitude of the complex vector in the complex plane times a phase term. So this term has a unit length, and the direction it's pointing is given by the phase theta. Um, so the question is a very interesting question. It's like, why on earth would e to the j theta equal cos theta plus j sine theta? It's like, what does e have to do with cos and sine, right? E, if you've taken, differential equations and you've looked at growth curves and things like that, E is this Euler's number, which is 2.718281824 or something like that. So it's a transcendental number. It's just a number. And you raise it to this power and you get cosine and sine. Seems a bit bizarre, right? It turns out if you write out the expression around the origin for e to the j theta, the Taylor series expression, you get something that looks like this. It's 1 plus x squared over 2 factorial plus x squared over 3 factorial, x cubed over 3 factorial, etc. Forever, right? This is the Taylor expansion for e to the x with just jx in there. Um, so when we square this, obviously this j squared is going to give us -1. And when we look at the Taylor expansion for cos and sine, uh, cosine around the origin is 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial minus x to the 6 over 6 factorial. So it's a very interesting pattern. These are all even numbers, but we're getting a minus and then a plus and then a minus. The only way to produce that sequence is by using something like j, right? But this is the expression for cos. This is the expression for sine. And if you plug j theta into those, you get this, right? And so it's a magical thing. But in some ways, maybe it's not so magical in that when I differentiate e, right, it's infinitely differentiable, right? It's a curve that always has a derivative, and that derivative is always the value of the curve, right? And in the same way, cosine is infinitely differentiable, right? So you can differentiate cos and you'll get minus sine. You differentiate that, you'll go back to minus cos. You differentiate that, you get sine. It just goes on and on and on, right? And so it's that relationship of this infinite differentiability that I think relates these two things. This is often called the most beautiful formula in mathematics, right? It's got all these fantastic things in there. If you so so this is just an explanation of Euler's formula written out as cosine and j sine. Okay. Now we're going to look at any questions on that. If you have questions, I think the best idea would be maybe if you raise your hand, I don't know if it'll pop up on the sidebar here. It might, um, is, or you could just interrupt me verbally. Uh, can somebody try and put their hand up and see if say, Noah, do you want to? Yeah, okay. All right. So that Noah Fox raised his hand. Perfect. So you can raise your hand if you have a question. Okay. So now we're going to look at plane waves. These are really important for all of imaging, and specifically MRI is all about plane waves that you impose on the sample before you actually listen to the RF coming out of the sample. So let's look at the easy algebra for this. So we have a function Sxy. It's a two-dimensional function in the plane. And I'm going to use this formula to describe that function. Okay, and this is a plane wave. If I set this mu naught constant here equal to 1 and nu naught here equal to 0, then all I have is sine 2 pi nu naught x, right? And for every y, it looks the same. I go across here and I have a sine wave with this frequency. right, with this frequency mu naught. If I double that number mu naught, I'm going to get a sine wave again with double the frequency, right? Per unit length on here. Quadruple, I get four times, etc. So I go to higher and higher wavelengths as I modify my wave vector or my, here. When I add in a component in the y direction, so now I've got four cycles this way, and if I go up in y, I have one cycle that goes through over the whole unit length here. It looks like a four cycle plane wave going in a different angle, right? And so it's like I've rotated that plane wave by adding a component in the y direction. If I add another component, I rotate it to a higher angle, another component rotated to a higher angle. And so now I have a higher frequency sine wave whose direction or plane wave direction is off at a different angle, right? Um, what we're going to, so this, it's important to understand that, remember, we can build two-dimensional uh, functions, so any kind of shape in two dimensions, by summing up different sine waves of different frequencies and in the two directions, right? So, or different angles, okay? Uh, so what is we want to mathematically describe our imaging system, okay? And so in the book, in Prince and Links, they say, okay, this is our function, input-output equation function for our imaging system, and they use this script S. For the rest of these slides, I'm just going to use bold S because I don't have this script S in PowerPoint. So anyway, if I have my object, this is my true object, I submit the signal from that true object to my imaging system and I produce this thing, this picture. Okay, so that's the picture that we're going to show the radiologist or whoever needs to see it. Okay. Um, so there's a couple of concepts that are super important when we think about about quantifying imaging systems with algebra and equations. One is the definition of linearity. So here's my imaging system, S. I'm going to put an input signal into S. It's from my object, right? And now I'm going to ask the question, if I put two input signals and sum them together into my imaging system, what happens, right? What a, a linear system, what defines a linear system is if when I do that, when I take two inputs, boom, boom, and I push them into my system, if I can take each individual input and put it into my system transformation S and add those results up right here. So this coefficient of weighting that was used like to make the composite system, if I put each individual one into the system and then I add them up outside here, that's called a linear system. Okay. And makes life a lot easier when we're trying to describe what's going to happen downstream when we have composite signals going into the system. So that's the definition of a linear system. Um, we can describe a system with basically an impulse response function. And we've discussed this before. And here's my script S system, my true fxy, which is the input to the system is over here. And recall if I make a little tiny dot and it's a delta function, then what I'm going to see out here is called the point spread function of this system. And as we'll see, the point spread function or the impulse response function is really the way we embody the system in mathematics. That's what we say the system is doing to our input signal, is it's creating an output image by by using these impulse response functions, added up in the spatial domain. Okay. Um, special type of impulse responses. So this is the equation, we'll say, for the impulse response. It is dependent on two variables, okay, eta and psi. And if the impulse response is not the same for every position in the field of view of our image, we need to identify that and say, look, I've got an impulse response. At each location, I have a different impulse response. That impulse response is still has values everywhere in the field of view, right, over all of these variables, but I need a new or a different impulse response for each point in the plane. That makes life a lot harder, right? So if I have a lens, and this happens with your binoculars, like if you have binoculars, you can look through the binocular and look at an object right at the center of where the lens is in the field of view, and you look at that and you bring it into focus. And now you just drag the binoculars so that you move to the outer part of the field of view. As I move to that outer part of the field of view, this impulse response function here, it changes, right? It usually gets blurrier and it can sometimes distort things out on the outside because it's really hard to make a lens that has a really nice flat image, right? However, if ideally what happens is we aren't dependent on X and Y, and that's called a shift invariant system, and we'll see that. Okay. So here's if I have a delta function is my object now. So I'm saying, okay, I've got my little bead and I'm going to put it into my imaging system. When I image it, what I find is my point or my impulse response function or my point spread function. And if I do that for each value xy of where that delta function is, then I can map out all of these different impulse response functions. So this is the fundamental sort of mathematical construct that is used to build images out of signals that your detector is seeing. So here is our input. It is defined on a two-dimensional space. I have a value, say, everywhere in that two-dimensional space. This is my imaging system impulse response function. And what we're going to do is we're going to compute a value of our output image at a specific point. So I asked the question, what is the value of my image at this point XY? To make it concrete, we could say, what's the value of my image at the origin, right? When X is 0 and Y is 0, how bright is my picture right there, right? So I set X and Y to 0, right? And I pull out that impulse response function. I have one impulse response function I know what it is at X and Y 0, and I perform this integration. It is my input, the entire thing, right? Not just at the origin, but the entire thing multiplied by my impulse response over the entire space, and I integrate that over that whole space. So my value at a specific point xy is determined by values everywhere over my input signal multiplied by the impulse response function. So if this impulse response function is really sharp and narrow and it only exists at a really tiny spot, that's the only thing that's going to get pulled out of my input signal and become the value over here. Okay. Again, we can do a couple examples. If this input signal is a delta function, right? My image is going to be an image of this darn thing, right? Of the impulse response function. And that's a way to figure out what your impulse response function is. When your input is some continuous function, you use these impulse response functions to see what blurred version of this you achieve. Okay? So if we can make the assumption that, oops, I'm sorry, I shouldn't have done that. Meeting my screen. There we go. If we can make the assumption that this function, h of x, does not vary with x and y, i.e., it's basically a constant shape everywhere in the imaging plane, then, oh man, I have two arrows. I don't know which one. This is probably the one you guys are seeing. So we can write down the impulse response function and just shift that response over the whole field of view without changing the function itself. So this is like if I have a specific blob that defines my point spread function, and that blob is spatially independent in the field of view, then I can use this as my impulse response function to do the hard work up here. Okay. Well, I seem to have messed this up. All right. Sorry, a brief moment here to try and get my screen back here. Okay. I think we're good. Can you guys see the screen? Can somebody verbally tell me they see the screen?
Yeah.
Yeah.
Okay, great. Thanks. Okay. So now let's go back to our superposition, and we're going to have our input image. This is our input data coming at us, right? And we will perform this superposition. But now, instead of having to have a different h for each xy, we'll use one h and perform this integral here. Okay. This is called a shift invariant point spread function, or a linear shift invariant system, or LSI. And it has fantastic properties that we will see. When you can model your system mathematically as this, your input convolved with a point spread function, makes life really easy. So this, for those of you who have experience with convolution, will recognize it as H convolved F, right? And so that G is just a convolution of the point spread function with the object. So your final picture is just your object convolved with the point spread function, and that's what you get. So it's usually a blurred version of your input object. So let's look at what convolution is quickly. So here's H and here's F. I've got two functions. We've dropped down to 1D to make this simpler. This happens in 2D for most imaging. It can happen in 3D as well for MRI and CT, actually. So the convolution formula, what it does when you look back at it here, you basically subtract, let's just look at it in 1D, subtract epsilon and you do, or eta here, and you do an integration across the sample after flipping your point spread function with this minus eta. You do that integral. And visually what that looks like is, here's my point spread function. I flip it such that it looks like this now. It looks like a backwards version of H. And now I do an integral, I multiply for each offset, right? Each offset of the function, I multiply H and F and get a value and plot that value. And then I shift again and I multiply F and H together again, and I get a certain non-zero value here, and that is the value of the convolution at that offset. I continue the integral, and now they're overlapped such that I get this area under here, it peaks out, and then as I move more, the non-zero area here gets mapped to there, and then finally I'm they're not overlapping anymore, it goes back to zero. So here's basically a ramp function and a top hat function, and when you convolve them, you get this thing. Looks like that. Okay. Convolution is used extensively now in convolution neural networks. That's why they're called convolution neural networks. And this is H, or the kernel or the filter that's used for the convolution. And our original image of, let's say, a cat that we're trying to figure out if it's a cat or a dog, right? You take that whole picture and you take a kernel, this convolution kernel, which is your H function, and you convolve the entire input image with that, and you get an output. Okay. Uh, we now have a reduced dimension, basically, of this uh, representation of the image. And you do that for many different convolution kernels. So you just change these numbers. You get to pick these ahead of time, and you change those numbers and sum up the convolution values that you achieve by doing this convolution. And you give a weighting value for each one of these convolution kernels. And then you essentially iterate over this technique and change those weightings until the performance of the convolution kernel, when it gets down to a very low dimension, says cat, right? Or dog. And so it's deeply involved. This convolution, imaging convolution is deeply involved in all the AI of imaging technologies at this time. And every one of your pictures on your phone has these things running through it, and basically going through and finding, you know, facial recognition and object recognition and all that stuff. And so when you put your phone in your pocket after taking pictures, it actually gets pretty busy and it runs a bunch of these tests and stuff to try and find, hey, did you take a picture of your sister? It's a little spooky, but that's how it goes. So linear shift invariant systems have some really nice properties. So if these are linear shift invariant transforms, I put my input signal into this one, do a convolution, I get an output signal, do a convolution, and I get G. It doesn't matter which order I do these two convolutions. I can take my input signal and do this one first, and then feed the output from that one into this first convolution, and I will get the same output, right? And the other thing I can do, if this is what's going to happen, and this is characterizing my system, one part of the system and another part, is I can just convolve these two things and call that one thing my system, right? That's true for linear shift invariant systems, okay? Uh, Secondly, if my input goes into one process and another process, and those two processes are added up, right, at the output stage to get my new to my image, then I can just feed the input into the addition of the the two uh, basically point spread functions. If you're super lucky, your uh, system can be characterized by a point spread function that can be separated in space and have separable variables. And this makes the mathematics obviously a lot easier, right? Particularly if you want to compute the output of your system, you can do it with two one-dimensional convolutions as opposed to having to do a full two-dimensional convolution. And these one-dimensional convolutions are much, much faster than two-dimensional convolutions, and so you gain a lot of speed. And so if our original input looks something like this, and we have a point spread function in the x direction, right, we can do that convolution and generate an output, which is W. We then take that output from this one-dimensional convolution and put it into a one-dimensional convolution in the y direction, and that gives us our final two-dimensional image. Okay, and here's an example of a very useful separable image. And so if I have a blob, this is a Gaussian blob in the XY plane. So it has a peak and then it rolls off. And so this is often used as a filter to roll off things that are outside frequencies you don't want or outside a field of view you don't want. So, but this thing can be modeled as obviously the multiplication of two one-dimensional functions that are completely separable. So that makes life easy. We can look at uh, that principle in pictures. So if I start with an input function, this is fxy, and it shows fairly high detail, and I convolve this with a convolution kernel or a point spread function in or impulse response function in X. So I take the two-dimensional thing and I perform these 1D convolutions. I get that W function here. And obviously it's blurred in the X direction. If I look at this edge here, and compare it with the sharpness of that edge, obviously it's a lot duller now. It just rolls off really slowly. However, when I look at the top of this person's head and I go this way in the vertical direction, it's still pretty sharp. I still have pretty good definition of this. And so that's because the convolution in X didn't blur this input in this direction. When I hand this image to the convolution in Y, so this is the vertical impulse response function. Then I'd get a true blurring in Y, and these details get all muddled, and the whole thing now is two-dimensionally blurred. Okay. Okay, so this is the key relationship of all mathematics for this course, I would say, and for most imaging, particularly for magnetic resonance. But as I said in the first lecture, I think this is a transform or a formula they should really understand really well. So I really encourage you to use Claude, ChatGPT, whoever you use, to just paste this thing in here and say, tell me about this. What is, how does this thing work? And it will usually come up with some really good examples and things like that. In addition to what I'm going to tell you in the next 90 seconds. So if I have a function in two dimensions, okay, it's a continuous, nice function, and I want to know what are the spatial frequencies that are represented in that function, okay? Let's think back to about 4 slides ago, right? And if I go, or maybe more than 4, I go here and I say, what functions are represented in this image? What spatial frequencies are represented in this image? Well, the answer's right here. Well, we have 4 cycles per unit length in X and 0 in Y. Those are the spatial frequencies that are represented here. And this is also an interesting picture. However, the spatial frequency now is in the Fourier plane has the position 4, 4, right? So it's basically one plane wave still, but it's rotated. But that's when I have a more complex picture, I can ask the exact same question, but I won't have such a trivial answer. In this case, I had a very trivial answer, and I have this is the one frequency that's represented in this image, right? So when I go to the Fourier transform and ask the question, okay, here's my Fourier space. What spatial frequencies, nu and mu, are represented in this picture? Okay. The way to do that is through this formula. You multiply your function, by this essentially phasor. This is a complex number that has unit magnitude but it has a phase shift that changes as a function of x and y in the plane, right? This, in effect, when you set mu and u here, you set a plane wave that is multiplied by your function, and then you integrate after that product, you integrate those two functions together. If they're very similar, it will give you a non-zero value, and you'll get a Fourier coefficient or a term saying that that spatial frequency is represented in your data. If this is the Fourier transform of this function, we can take the inverse Fourier transform of it, and it looks exactly like the Fourier transform, except instead of a negative sign here, we have a positive sign. We do the integral in Fourier space of this inverse Fourier transform, and we get our function back. This is the raw data for MRI, as you will find out, all right? And this is the simple way of reconstructing that image, is when we get our raw data, we take this inverse Fourier transform, we get a representation of the underlying object. Let's do that integral. So here we're going to reduce to one dimension now to simplify things. And this is the 1D Fourier transform of this function g of x. Here's the argument. Remember, we're going to, instead of that mu value, we're going to call it k sub x, because this is the notation of MRI. So this is still a spatial frequency in cycles per centimeter. This is position in x. So we're going to integrate across gx. The first thing we'll do is we'll say, what frequency component are we going to evaluate here? Let's set kx to that component. Say it's 4 cycles per centimeter or something. We'll set that and ask, what is g at 4 cycles per centimeter? Put 4 in here, run this integral, right? So this thing oscillates up and down with a certain frequency as x changes, and pulls out whether or not g of x looks at all like that oscillation. To actually perform that integration, you can break it up into its two components. Here you have g of x cosine and g of x sine, okay? And you ask, what part of g of x looks like cosine of this frequency, right? So here's an example of a function which we've seen before, and this is a square wave function that essentially goes between 1 and -1. It has a length, a full periodic length of 1, okay? And we can ask, what are the first 3 harmonics or 3 spatial frequencies that are used to create a representation of this square wave? So here they are. There's the primary, right? This is the first harmonic that goes through one cycle sinusoid and peaks at the middle of our square wave here. This is the third harmonic, comes through here, this green curve, we add that in, and then the fifth harmonic, we can add that in here. If I add those up, I get the blue curve, which is getting closer to being this square wave function, right? And as I add more and more higher frequencies and their amplitudes drop, I will get closer and closer to representing that square wave adequately. So let's look at what happens when you take the Fourier transform of basically the square wave function. Okay, so now how do we do that? Here's our function. So this is that g of x that we were talking about. So it's a very simple function. It's 1, right, all the way out here, and there's -1 all the way over here. But we're just going to look up to here when we evaluate this integral. And I set my kx to 1, right? And so that's this red curve here, right? And I In that, so this is the phasor that e to the 2 pi kxx is this function right here with kx equals 1. When I multiply by g, I get a non-zero value, right? So the integral of the product of this is just the integral under that half of the sine wave, okay? When I look at the second harmonic, okay, so now I flip my k to 2, and I look at the second harmonic and ask what's the integral achieved when I multiply my g of x with that phasor and do the integral, okay? So I get a positive value here, integrated up to there, and then I get the exact same value but negative here. So that integral is 0. So that tells me that in this square wave function, this frequency is not needed to build that function, okay? Because the Fourier component is 0. And that integration just told me that, yep, it's gone. I don't need that function. When we get to the third harmonic, and you can see how this is going, I integrate under this part of the curve, because this is 1, remember? And then I integrate under this part. Those two cancel out. So I'm back to 0 in terms of my integral. And now I have a bit left over. So I'm non-zero. I'm whatever that integration is there, right? So the third harmonic will have a value in the Fourier transform. Let's look at the fourth harmonic. You can see how this is going to go, right? So I integrate to here, I get 0. Integrate to here. Oh no, sorry, I'm on the wrong one. Sorry. Integrate the blue curve to here, I get 0. Integrate to here, I get 0. So fourth harmonic, not needed, right? Fifth harmonic, I integrate to here, get 0. Integrate to here, get 0. And then there's a little bit left over. So the fundamental frequency, third harmonic, fifth harmonic are used to be summed up, right, and create this square wave function, okay? The relative amplitudes are the values of those integrals that we just calculated, and they're given here. The amplitude drops as the frequency gets higher. And when they're added in, we get closer and closer. Okay. Units. Oh, okay. So the point of this is many of you, if you've done Fourier analysis before, you may have done it in the context of essentially audio or E&M. And so oftentimes G of t is the function, and it's a time domain function. And so you could take a microphone and a preamplifier and you have somebody, play a flute, and then you plot the voltage as a function of time, and that's your G of t, right? And then the frequency component there is literally in hertz, right? So it's cycles per second. It's like sound frequency, right? Or if it's an electronic voltage, which isn't a sound, it's still hertz, right? The interesting thing is if I take the flute and I plot G of t and I look at the curve, and then I take, say, I don't know, clarinet, and they both play the same note, right? Say it's A440, and I look at G of t for the clarinet. When I look at the two time domains, I probably will see some difference, but it might be subtle. When I take the Fourier transform of those two time domain signals, the Fourier coefficients will be quite different. The spikes, I still have an A440 spike, but it's the overtones at the higher frequencies that come out that give you the characteristic sound of that instrument. And so that is where the Fourier transform comes in. You can say, look, the Fourier transform of that signal looks like this. So now, to make a flute digitally, all you have to do is carry around those relative amplitudes. And say, anytime I need a flute, I'll just make a sound that has these relative amplitudes. It'll sound like a flute. That works kind of okay, but it's, yeah, those electronic pianos that you had sort of, oh, here's the flute button. You play it, and it's like, eh, it sounds like an electric flute, but anyway. We're going to be mostly looking at spatial variables, so it's like an image in space, right? And then the spatial frequencies are essentially our Fourier harmonics are in the spatial frequency domain in cycles per centimeter. Okay. Um, some very important transforms, and you can do these yourself, as an example, just compute these integrals. But the Fourier transform of a delta function. Oh, Matthew, you go ahead if you got a question.
So, sorry, I don't know if we're gonna be covering that, but with your example of the flute versus clarinet, if they play similar songs, are we gonna go over, for example, how to say, okay, these two sections of the song overlap, even though the song might have been different?
No, we won't. We won't go over that. Um, so that's an interesting, more complex function, right? G of t, in that I have an instrument being played, but then I am modulating the amplitude of that instrument to make the song, right? So the modulation, we'll think about that. It will occur to us. But the example I was trying to show there was that in the fundamental time domain signal itself, there are these complex Fourier coefficients that give you the characteristic of that instrument. That's one role or one use of the Fourier transform. But we're not
Gotcha.
going to, we'll look at images that are blotchy and things like that, which might be one way of thinking about it, but I would just let that go, not think about it. Did that answer your question?
Yeah, thank you.
Okay, good. So let's look at some Fourier transforms. Um, what is the Fourier transform of a delta function? Well, here's the equation. So we put g of x as a delta function, right? Here it is. And here's my phasor, and I'm going to do this integral. And I invite you to do the integral. And it turns out that when you do this integral for any value you want to put in here for kx, the integral comes out to 1. And so what does that mean? That means in a delta function, all frequencies are represented equally. Okay. So the Fourier transform, like the frequency coefficients of this function, which is a really tall spike, is equal representation of every frequency, right? Which seems kind of impossible because you would have infinite power, right? So basically, that's for a true mathematical delta function. What is a delta function in audio is like if you're listening to an old turntable type system and there was basically a little crack in the groove on your record. When the needle goes across that crack, it makes a very large pop, right? That's sort of a bang delta function sound, and all frequencies are required to like make a really sharp pop, right? If that delta function is shifted, right, in space, right, we can put that shift in here. The Fourier coefficients still have unit amplitude, right? So regardless of the frequency kx, they have the magnitude of this phasor is 1. So it's 1 for every frequency. However, the phase depends on where you are in spatial frequency times whatever this offset was. Right. So this now gives you a rate at which the phase is changing in k space, right? Is whatever that offset was. If we look at the Fourier transform of a rect function, remember in the Fourier transform definition, the integral goes from minus infinity to infinity, right? Well, a rect function, we know we don't have to do that whole integral, so we can go from minus a half to a half. And we know that the function is 1, right, for the rect. So that's just the integral of that phasor, right, from minus a half to a half. And you can do that. You can just look that integral up, and it's equal to this, right? And it's e to the I j pi kx minus e to the I positive j pi kx divided by this argument kx. This thing turns out to be the sinc function. Okay, so when you simplify this, so you go, when you simplify this, it's sine pi kx over pi kx. Okay, so it's the sinc function, and we've seen pictures of that function a lot. So here's our function delta x at the origin. So if I have this and I ask what is its Fourier transform, it's just this, 1. Everywhere it's the same, right? And here, with the delta function shifted across, I now have a unit amplitude function, but its phase changes as I move in kx. Okay, and the rate at which that phase is changing is proportional linearly to how far away from the origin this is. Um, okay, we just looked at that. So here's the picture of the rect function and its Fourier transform. And the inverse Fourier transform, obviously, of this is the rect function. What else do we have? Oh, the Fourier transform of a phasor that is oscillating, at a frequency k naught x in the spatial domain. When I take the Fourier transform of that, I get a delta function, a single frequency, a kx. No, I'm sorry. It's at it's a single frequency at the offset k naught, which is this point here, right? So it's a delta function with a shift to k naught. So it's a single spike in the Fourier domain. Different than that, if I take the Fourier transform of a cosine function, right? I actually get two delta functions in the Fourier domain. I get one at the frequency positive k naught, right, in the Fourier domain, and I get another one at negative k naught. So positive k naught and negative k naught. Okay, and the power goes halfway to each of those. And the reason is, if you look at cos the cosine function, really you can't tell whether or not the function is going in the positive direction or the negative direction, right? There's no way to determine. Like if I'm sitting at a point and I'm watching a cos function go up and down, I don't know whether that function is traveling, that wave is traveling to the left or to the right. It's just going to be producing the same signal. So you say it's traveling both ways, and you throw a half from each. Similarly for sine, except we have uh, the complex rotation of it. Um, so this is just how you uh, do these integrals by plugging in sine and cosine. Okay, linearity. Um, we looked at one definition of linearity when we looked at our system function, and we had a summation of inputs. And we said, oh, we can put each input through the system function and then sum those outputs. And that's equal to summing all the inputs and putting that sum into the imaging system. This is mathematically saying the same thing, and that is if I have the Fourier transform of a sum of two functions, right, with the coefficients a and b in front of those functions, all I have to do is take the Fourier transform of the individual function g, and that becomes this cap g function here in the Fourier space, and the Fourier transform of h, that becomes cap h in the Fourier space, and the amplitudes add up in exactly the same way. Okay, so that's what we looked at before. Um, and it works in 2D, it works in ND, right? Um, okay. So if I have the definition, this is our Fourier transform definition, and I have a Fourier transform of a phasor. So this, you can think of this as a vector, a unit vector in the complex plane, spinning at a specific frequency, AX. Okay. So when I take that Fourier transform, I get a delta function at this single frequency A, right? If I take the Fourier transform of this, right, I get the phasor back, except it's spinning in the opposite direction, right? So this is I need to take the inverse Fourier transform to get back to this. If I just take the Fourier transform of this, which is this function here, I get a similar phasor, except it's in the opposite direction or the opposite frequency. And this is called duality. And so that is if I have a Fourier transform, right, gx, and I take its Fourier transform, then what I get is that Fourier transform of g, which is this little g, but I have to reflect the output around the origin. Okay. Okay, so application of duality. So if we're asked on a problem set or something, please compute the Fourier transform of sync. And then when you write down the formula, you plug sync into the Fourier transform formula. So this is our g of x in the formula. And then this is the phasor. Well, this integral looks pretty tough, right? And we could write out sine x as exponentials and everything. It's going to take us a long way. However, we know that the inverse Fourier transform of sinc x, right, is a rectangle function, right? And we know that the rectangle is the Fourier transform of a rectangle is this sinc function. So then we should be able just to say, oh, okay, well, if the Fourier transform of a rect function is the sinc, the Fourier transform of sinc is the rect function flipped around the origin, right? So therefore, the Fourier transform of the sinc function is the rect function flipped around the origin. However, the rect function itself is symmetric, therefore it's just the rect function, okay? Because those two are equal. Okay, so some basic Fourier transform pairs. Uh, and this, you should really know this whole chart. It seems like a lot. There's a lot of letters here, but it's not a lot of concepts really. And so the signal is here. It's one. So it's all spatial frequencies represented, say. So if I have a signal of one and I take its Fourier transform, I get a delta function, right? If I take a Fourier transform a delta function, I get one. Okay, so they're nice symmetric pairs. Okay. The Fourier transform a delta function that is offset in the plane gives me a phasor which has a uh, frequency that is equivalent to that offset. Okay. This is a interesting function. So if I have delta functions, so this is a continuous function. It's defined at all values of x and y continuously. Most of the time it's zero, but at these intervals, we have spikes, delta functions that are up. When I take the Fourier transform of that, I get basically a set of spikes again, a comb function. And those spikes are separated in with this frequency here. So mu delta x. So these give you the rate at which those spikes are happening. Um, this is just a complement of this. So we've done that. Sine of a plane wave, right, is equal to delta function uh, at 2 points in the complex plane. Okay, cos the same way, delta function at 2 points in the complex plane with the frequencies defining where those points are. The Fourier transform rect function is sinc. Fourier transform sinc is rect. Comb goes to comb, and Gaussian goes to Gaussian. Okay. So those, it's like a dictionary or of pairs. You can draw little diagrams of what those things look like as an exercise such that you can remember them. And just keep that with you. And then here's some fundamental properties of the Fourier transform. Um, so here we've got a signal fxy. It's a continuous signal in the plane. Its Fourier transform is this function. And here's gxy and its Fourier transform is this. So that sets us up so that we can start looking at some properties. We already looked at linear, what a linear system is, and we saw that the Fourier transform is linear, so that I really only have to know the individual Fourier transforms to get my sum. We just looked at translation, so the Fourier transform of a function that's translated is the original Fourier transform multiplied by this phasor. So that's kind of very convenient. So if I'm looking at my image and I take its Fourier transform and I get f mu and v here, then I take the image and I go, oh, the image got shifted like whoop, in the plane. Then I don't have to recompute the whole Fourier transform. I know that it's the original Fourier transform just multiplied by this phasor that is proportional to the offsets in the plane. Oh, this is a really good one. Conjugate. Uh, so if I have a function in the plane and I take its conjugate, then because if it's a complex function, I look at its conjugate, then I know the Fourier transform is the conjugate of the Fourier transform of f, but flipped around the origin, reflected through the origin. So it's mu, negative mu, positive mu. Okay. This is very useful in MR when you're thinking about raw data and things like that, like what happens when I look at the conjugate of my uh, image. So, and here, if uh, f is real, i.e., there is no imaginary component, so there's no phase to your pixels. They're all real valued pixels, which in MR is not true. In MR, every pixel has an amplitude and a phase associated with it. But you can limit yourself. You can say, I really want a real valued image, and so we'll try and make one. But we know that if fxy is a real valued image, then the basically the Fourier transform is symmetric around this flipping across the origin. Okay. So if I'm at mu v, so here's my space. If I'm at mu v and I have the Fourier transform over here value, I know it's equal to the value flipped around the origin over here. That's if it's a real valued function. Signal reversing, if I flip both directions in my image, then the Fourier transform just flips with it. Scaling, if I scale the axes of my image, if I like shrink down the x-axis or something, then with this coefficient a, then in the Fourier transform, I'm going to expand in that Fourier dimension with 1 over a, and I need to also normalize the Fourier transform to take care of the power. Rotation is cool. So if I have a function and I rotate it in the plane, so here I have an image of a head, say, and I rotate that head 45 degrees because I want to look at it this way for some reason. Then you ask, well, what's the Fourier transform of that thing rotated 45 degrees? It's just the original Fourier transform rotated 45 degrees. Okay, so rotation just goes. Um, and then here's the big one. This guy here, we worked hard to figure out what convolution was. And if I have basically an image and I convolve it with this function gxy. So this, let's think of it this way. This is an image, and this could be a filter, say, but it doesn't have to have that interpretation, but that's more likely what it's going to be. So I have an image and I convolve it with this thing. When I take the Fourier transform of this convolution, this is what it equals. It equals the Fourier transform of f times the Fourier transform of g. That's ridiculous. That's so convenient, right? Is that if I want to convolve my image with some filter kernel, say it's a Gaussian and I want to blur my picture, right? And I can run that two-dimensional convolution, or I can take the Fourier transform of my image, the Fourier transform of that blurring kernel, and just multiply them in Fourier space. Just do that multiplication once, and then take the inverse Fourier transform of that thing, and I get this, right? That's terrific. And it works both ways, right? Though in Fourier space, if I convolve my Fourier transform with something, this thing, then it's just the product in space. Okay, Parseval's theorem uh, tells us that if my power under my image fxy, so fxy is non-zero, it's got some power. When I look at the amplitude of each point squared and integrate that whole thing, that gives me a number, a non-negative positive number that is like how much stuff is in my image. So if there's lots of brightness, I get a lot of stuff. It turns out if I look at the Fourier transform and do that same operation, look at its magnitude, square it, and integrate over all of Fourier space, I get the same number. So that means the amount of power or stuff in the spatial domain after you take the Fourier transform is preserved. So you've got the same amount of power and stuff in the Fourier domain. It doesn't shrink down, doesn't disappear, or something like that. Okay. And oh, we did convolution. Okay. So here's a method of just convincing yourself that this convolution theorem is true. Yeah, you're welcome to go through these steps. We just write out what is the convolution, right? And pull this out of the integral and do this, and it leaves you with basically um, an expression that boils down to the product of those two things. Um, so this you should remember that, okay? Just the big thing to remember is the Fourier transform of G convolved with H is the Fourier transform of G times the Fourier transform of H, okay? Think of it as a filter. If I want to filter out high frequencies, and this is my Fourier representation of my object, and so the high frequencies are the values of K that are large, then I would have an H that as I move to large values of K would roll off. Okay, and that would be a filter. And it would attenuate those high frequencies. That's equivalent to using a kernel over here in the convolution that blurs pixels together. And so here's, if you recall, we looked at the modulation transfer function, remember that guy? And we we know that the modulation transfer function is the result of the Fourier transform of the point spread function. And so I can plot the modulation transfer function as a function of spatial frequency. So in this example, this would be the modulation transfer function. This would be our point spread function, right? And if the modulation transfer function is 1, 1, 1, 1, 1, 1, 1, it passes all frequencies. And what is the inverse Fourier transform of 1, 1, 1, 1, 1, 1 everywhere? It's a delta function, right? So we would absolutely replicate, right, the input object as our image, right? If our modulation transfer function was 1 everywhere. However, physical systems don't work that way. Eventually, you run out of resolution because things get averaged together. And so the modulation transfer function literally rolls off at higher frequencies. And when you take your Fourier coefficients of your object and you multiply by that roll-off and take the inverse Fourier transform, that gives you, the resolution of your imaging system. You get to choose where to do this because, I can always, if I start here, right, this is what my system is doing, and the radiologist comes to me and says, you know what, it's too noisy. There's too much signal at these really pixely high frequency values. It looks like hash. I really don't want to see those hashy pixels, please. Then you multiply your Fourier transform of your image by this, inverse Fourier transform, go back, and all of that hash is gone. All the hash is gone, but also your edges are a little blurrier because we don't have those higher harmonics to make the really sharp edges, right? Remember how we made the square wave sharper and sharper? If we cut it off, we say, that's it, we're done with sinusoids at this point, then it can only make edges so sharp, right? And here's an example of a two-dimensional function. We'll call this gxy. Its Fourier transform looks like this, right? This is the magnitude of the Fourier transform has magnitude and phase, but we're ignoring the phase and we're just going to plot the magnitude of the Fourier transform of gxy, which is this guy. Oftentimes, you not only just you plot the magnitude, you plot the logarithm of the magnitude because the values around the origin are so much higher than everything else. You need to compress it to actually see what's going on out at the high frequencies. If we take this HX approach, we go back here and we take an HX that rolls off higher frequencies like this, it rolls off these higher frequencies. When we multiply by H of KX and KY here, then the data goes from this to this. All this stuff out here got multiplied down to essentially zero. So the high frequency components out here are not represented anymore. There's no data. And then the picture, when you take the inverse Fourier transform of this data, you get this picture, right? And it's obviously just a blurred picture. It is, in fact, this picture convolved with the Fourier transform of whatever the shape was of the filter that you multiplied out here. Now, here we go even farther. We might, multiply even down here, right? So that it's a much sharper or a filter that eliminates more high frequencies. So now I have no data out here. And I take the inverse Fourier transform of this thing and I get this picture. Okay. And last year someone said, look, if you have this picture, why would you ever make this picture? And the answer to that question is this picture might take you 5 minutes. This picture might take you 5 seconds. And therefore, if I want to measure something that's happening every 20 seconds, I probably want to take this picture, right? And I might not be able to resolve in great detail what's going on, but if I want to resolve some part of the brain that's changing its amplitude on the order of, 5 seconds, then I'd use that picture. I would use this to figure out what the heck is underneath this, right? These could be just put in color on top of this or something. So that's why you can trade off, or why you would trade off resolution, right? For time, for example. Okay, that's it. Are there any questions?